Hello and welcome to the 18th September HSC Maths Extension 1 revision lecture. So glad you came to join us today. We are going to revise the Extension 1 syllabus today. Thanks so much for coming. So at this point in your studies, you should be familiar with what 18 Notes is, who we are. In case you haven't, in case you're brand new and just watching one of our lectures for the first time, we're an educational company run by former students for students. And our ethos, our goal is all about accessible education. So we aim to provide quality resources to help students like you thrive and succeed in your HSC. So we offer a bunch of resources to do this, including these free lectures that you're watching right now. We run these lectures every single holiday series, and this will be the final lecture series before your actual HSC exams next month. Okay, so some of you may already know me if you've already been to one of my lectures before, but in case you don't, my name is Leo and I am your lecturer today. I've been working at 18 Notes since 2019. I graduated in 2018, so it's been 5 years since my HSC. It's gone by so quickly. I achieved a band 6 in all my subjects, including 4 units of maths. So I did a mixture of subjects across STEM and humanities. So my subjects are listed here. You can see I did biology, business studies, advanced English, extension 1 maths, extension 2 maths, and also modern history. I love maths. It was one of my favorite subjects at school. I managed to get a mark of 99 for extension 1 and 93 in extension 2. So we know if you do extension 2, they give you a mark out of 100 for both extension 1 and extension 2. If you only do extension 1 with Maths Advanced, you'll get a mark out of 50 for extension 1. It's one of those weird subjects where you get a mark out of 50 or a mark out of 100. And I achieved an ATAR of 99.45. So I am currently studying a combined arts and law degree at the University of Sydney. I'm in my second last year. Next year will be my last year. I do enjoy cubing. I can solve from the 2x2 all the way up to the 5x5 cube. It's so therapeutic being able to solve a cube. I really love country music, and I love the banjo so much that I'm currently learning how to play it because I just love country music that much. The sound of it's awesome. And I also enjoy playing the video game Valorant, although I am not very good at it. So shout out to anyone else who has similar interests. All right, so this is your current status. This is your current situation. Your HSC Maths Extension 1 exam is set for the 20th of October on Friday. And that is less than a month away now. So from the live premiere of this lecture, it's actually exactly 23 days away. So I did a maths, I calculated it for you. From today, it's going to be 23 days away. So you've completed all your assessments at school. You've had most of you would have had your graduation ceremony by now. And the only thing left is your actual HSC exam. And once that's done, you are completely free. You have the freedom of post-HSC. That's really one of the best time of your lives. So really make sure to enjoy it once you've finished the HSC. So the only thing left is the actual HSC. It's standing in your way. So this lecture, the goal of this lecture is actually to prepare you for the exam by covering different types of questions for the HSC Maths Extension 1 topics. And I'll be giving tips and tricks along the way as well. So this lecture is focused on problem solving skills using real HSC and trial exam questions. So it's more sort of question orientated. It's more focused on solving questions. If you do want more content specific sort of slides and content specific material, I recommend checking out the previous lectures we did in the year, including the January, April, and July series. That's where we went through the substantive content. And you can actually access the recordings to those lectures on the 18 Notes website. Today, we are all about sort of skills-based and applying our knowledge to different questions. Okay, so just a quick check-in with you guys. So this is sort of a good sort of framing, a good sort of framework that you might want to apply to answering a question. So when you do sort of go in an exam and you first come across a question, you kind of want to look at the question and sort of understand what the question is asking you. So sometimes they might have implicit information given in terms of the wording of the question. So note that down. For example, if they say initially a particle was at blah, 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 they don't explicitly say that's when t is equal to 0, but that's sort of the information it's conveying. Sort of see what information is sort of given in the information, and also what assumptions are underlying that question too. Also, make sure you pay attention to what the question is actually asking you to find. So sort of take note of what your final answer needs to look like. For example, they might be like, express y as a function of x. So in that case, you would have to take note that your final answer will be y equals some function of x. So you want to make y the subject. So other times they might be like, what is the acceleration of this particle or something like that? And don't give velocity, you want to give the acceleration. So make sure you take note and read the question carefully to see what they're actually asking you to find. So after you sort of understood the question, you want to start recalling sort of your formulas, your methods, and sort of what you've learned about in the content in terms of the methods of what you need to do in order to get where you need to go. So recall your relationships, recall your formulas and your methods. And then you want to start methodically solving the question step by step down a page. Make sure you are comprehensive with your working, show all your steps, don't skip steps, and solve it methodically. And afterwards, you want to double check your answer, make sure it makes sense, and that sort of your steps are written correctly without any silly mistakes along the way. Okay, so let's take a look at your HSC exam structure now. So this is what your paper will look like. It's a 2-hour exam and you'll have 10 minutes of reading time. So this is in contrast to the Maths Advanced or the Maths Extension 2 papers, which are 3 hours long. You should be familiar with this when you sat your trials. And instead of being out of 100, it'll be out of 70 instead. And up to 30% of the exam can be Year 11 content. So if I've actually done a sort of content analysis of the past HSC papers, and I can tell you that it's around 30%. So in the 2020 HSC paper, it was actually exactly 30%. In the sample paper, it was like 28.57%. And in the last 2 years, it was 27.14% of content coming from Year 11. So around 30%. And it's split into 2 sections. Your first section is a multiple choice section, which is worth 10 marks, and each question is worth 1 mark, and they're multiple choice. And in the second section, you have your short answers. So these are 60 marks, and it'll be across 4 questions, questions 11 to 14. And each question is worth 15 marks, but they're broken down into sub-questions. For example, you have question 11A, 11B, 11C, etc. And those can be broken down even further into part 1, part 2, etc. Okay, so this is your syllabus. You should be familiar with it. We know the syllabus is your best friend and you should treat it like your Bible. So in Year 11, you learn about functions, trig functions, calculus, and combinatorics. In Year 12, you did mathematical induction, vectors, trig equations, calculus, and also the statistical analysis topic. So we're going to go through every single one of these areas, Year 11 content, as well as each one of these Year 12 topics. So 6 areas we'll be looking at, and we'll be doing sort of real questions from previous HSC or trial paper exams. Okay. So let's go and have a look at Year 11 content, and make sure you do not forget Year 11. A lot of the times I find students, a common mistake is they neglect Year 11. They only revise Year 12 only to be surprised when Year 11 comes up in the paper. You want to make sure you are brushing up on your Year 11 content as well. Like ask the class of 2020, like see what happened in 2020. Look at question 14. If you know, you know. If you know what I'm saying, you know. Okay. So here's a question from the North Sydney Girls 2020 trial paper. So we are given the sketches of the following functions: y equals f of x and y equals g of x. And we're asked what is the range of the function when we divide f of x with g of x. Okay, so a common mistake that I see students make when they sort of attempt a question like this is they note that here we've got 6 and we've got -2. So when you do f of x divided by g of x, we will get -3. And at the end here, this is 12. The function is 12, and at the end, the function here is 3. So 12 divided by 3 is 4. So they say that it's what the range is that it's from -3 all the way up to 4. So they'll do, yep, this should be square bracket. They do something like that for the range, and then they select B. And teachers know that that's a common sort of line of thinking that people might do, hence why they even provided this as an option. But it's not right. B is not the correct answer. You want to actually consider exactly what's going on in the graph, not just to look at the endpoints to see what the range is. First of all, we notice that g of x here, when x equals 2, the function is equal to 0. And we know we cannot divide by 0 in a fraction. It's undefined. So we know when we actually have when we have 2 here, it's actually going to be a vertical asymptote because we can't divide by 0. Okay, so we take note that at this endpoint, 6 divided by -2 is going to be -3. Oh yeah, did I say 3 early on? I meant -3. Yeah, it's 6 divided by -2 is -3. -3, 4. Yeah, okay, so not that. So it's -3. Like so. But let's consider what happens as it goes closer to 2. Here, g of x is a negative number, but it's really close to 0. So like -0.0001, for example. And here, it's like something like 29.999 or something like that. And when you do 29.999 divided by like a really small number, -0.0001, it's going to be a really huge negative number because when you divide by a really small number, you get a really big number. So we know that it actually approaches negative infinity as you go closer towards here because it gets smaller and smaller and smaller. When you divide by a really small number, it will become a really large number. And since it's negative, positive divided by negative is negative. Here, the same logic applies, but it's on the other side. It's over the x-axis now, so it's positive like 0.0001. So it's actually going to be a really big number when you divide like 29.999 with 0.001. It's going to be huge. So the closer you get to 2, the bigger it's going to be. And here at the end, at 3, we have 12 divided by 3, so this will be 4 at the end point there. So we know it actually looks something like that. So the range actually is y is less than or equal to -3 or y is greater or equal to 4. But how do we actually notate that using interval notation? Well, it's negative infinity to -3, but inclusive of -3. And we have our other section, which is y is greater than 4, but all the way up to infinity, but not inclusive. And it's or, so we're taking the union of these two intervals. So it's actually going to be A is our answer. So you've got to be careful. Make sure you consider there's an asymptote here because you can't divide by 0. Okay, so here's another question. In a barrel, there are 50 marbles of various colors. Of these, 5 are green, 17 are blue, 12 are yellow, 12 are purple, and 4 are orange. What is the least number of marbles that can be selected from the barrel to ensure that 7 of the selected marbles are of the same color? So technically here, you could use the pigeonhole principle. This is a pigeonhole principle question, but you can also solve this question using common sense, which is sort of like you can just do it logically. So the way to do these questions, since you need to guarantee what is the least number of marbles to guarantee to ensure that 7 of the selected marbles are of the same color, you just kind of want to think of the worst case scenario of what could go wrong. So let's say we select 5 green marbles first. Obviously, you can't have 7 green ones because there's only 5 of them. And then afterwards, we select 4 orange ones. And we still don't have 7 because there's only 4 orange ones. And then let's say our next one we pick 6. Let's say we pick 6 blue ones. Then we pick 6 yellow ones. and then we pick 6 purple ones, we still don't have 7 marbles of the same color, because this is our worst case scenario. We've already picked 5 green, 4 oranges, 6 blues, 6 yellows, then 6 purples. Now, here's the thing. With our next marble, no matter what we pick, because we've already had our worst case scenario, our next one will definitely guarantee we have at least 7 of the same color, because we already have 6 blue, we already have 6 yellow, we already have 6 purple, we've already gotten all the other colors. So the next one will guarantee we definitely will have 7 of the same color. So you just add that all up, 5 plus 4 plus 6 plus 6 plus 6 plus 1, and that gives you 28 marbles. So you need to select 28 marbles to guarantee you definitely have 7 of the selected marbles being of the same color. And of course, you could have picked less than 28 and got 7, but that doesn't guarantee you definitely got 7. Here with 28, that's the least number that will guarantee you will always have at least, that you will always have 7 of the same color. Okay, so let's talk about this question now. So we're given y equals 2 inverse cos x over 2 minus 1, and we're told to state the domain and range of that function, and also and hence sketch the graph. Okay, so you should be familiar with the shapes of the normal inverse functions. So we know with inverse cos, it usually looks like this. It goes from -1 to 1, and here that's pi, that's 0, pi on 2, and that's 1, 0. Okay. So to find the range, we know that with inverse cos, when we put anything into the inverse cos, the whatever thing we're placing into inverse cos, sorry, not theta, inverse cos x, like I'll just use like a for a letter. Anytime we put inverse cos, anytime we put something into inverse cos, that thing must be between -1 and 1. It's undefined otherwise. So therefore, that means we know that that x over 2 minus 1 must be between -1 and 1. Because anything you put into inverse cos must be between -1 and 1. Otherwise, it won't exist. It will be undefined. So now we can solve this inequality. So we can say, we can add 1 to everything. So we can say 0x over 2 is between 0 and 2. And hence, x must be between 0 and 4. So this is our domain now. But we also need to find a range. So we note that with inverse cos, even no matter what you have inside, inverse cos itself will always be between 0 and pi. So that means 2 inverse cos x over 2 minus 1 must be between 0 and 2 pi. So therefore, we got our range. Our range must be between 0 and 2 pi. So this is our domain. This is our range. Okay, so now we can hence sketch the graph. So remember with transformations, when you are considering sort of horizontal shifts, horizontal translations left or right, you need to consider what's happening to the x directly. So here, the -1 isn't actually impacting x itself. It's impacting x over 2. So what we have to say is we can factorize out a half. So we can say this is 2 inverse cos half x minus, and this will be -2. So we know it's actually been, so what's happened to this graph? It's been shifted to the right by 2 units. It's also been horizontally dilated by a factor of 2, and it's vertically stretched by a factor of 2 as well. So we know that the domain is, so it's been shifted to the right by 2, so we know it's going to be between 4 and 0. And the range is between 2 pi and pi. So we know it's going to look like this. So here, this is the x-intercept. Here we know this is 2 pi, and here we know this is 0, 2 pi. So it's been shifted to the right by 2. So instead of being at 0, where the sort of middle point is. It's at 2 now because it's been shifted right by 2, but it's also been stretched horizontally by a factor of 2 and also stretched vertically by a factor of 2 as well. So instead of going from -1 to 1, it will be from 0 to 4, like so. Okay, so this is a polynomial question. So when the polynomial p of x is divided by x minus 2 and x plus 1, the respective remainders are 5 and 8. So we're asked, what is the remainder when the polynomial is divided by both of those things multiplied together? Well, okay, so we know that we have a polynomial. And we can divide, we are trying to find what we get when we divide x minus, what is the remainder when we divide this thing by x minus 2, x plus 1. So we know this thing here is a quadratic. So when we divide a polynomial by a quadratic, we'll get a quotient, which we don't know what it is, as well as a remainder. Now, remember that when we divide, the remainder is always going to be a polynomial with a degree 1 less than whatever was the divisor. So here's if you divide by a quadratic, your remainder will be a linear polynomial. So here you can write it as ax plus b, where we don't know what a or b is. So when you divide by a linear factor, you'll get a constant because that's 1 degree less. So when you're dividing by a quadratic, it'll be a linear. So it's 1 degree less of whatever you're dividing it with. Now, we know that when you divide it by x minus 2, the remainder will be 5. So therefore, we can say, using our remainder theorem, that p of 2, which will be, and this thing will be 0 times 3 plus 2a plus b. We know this will be equal to 5. And because this is 2, this entire thing will be equal to 0. So we can say 2a plus b is equal to 5. Okay, so now we can also say when when we put in -1 into here using the remainder theorem, this will be q -1, this will be -3, and this will be 0. And this will be -a plus b. This will have a remainder of 8. So we can say -a plus b is equal to 8. Okay. So now we have 2 equations, and we can sort of solve them simultaneously. So I noticed both of these have b terms, so I can do equation 1 minus equation 2. So this will give me 2a minus a, which is 3a, b minus b, which gets cancelled out, 5 minus 8, which is -3. So I can say a is equal to -1. And then I'm running out of space here, so I'll go here, sub 3 into 2. So I can say -a minus 1 is equal to 8. So therefore a is equal to wait, sorry. I'm subbing a. I found we already know what a is. It's equal to -1. So I can say sorry. I can say minus 1 plus b is equal to 8. Okay, so therefore b will be equal to 7 because 1 plus b is equal to 8, so b must be equal to 7. So therefore the remainder is ax plus b, so this will be -x plus 7, which in other words is 7 minus x. So that's going to be option A. So yeah, just revise, make sure you are on top of your remainder theorems and sort of your knowledge about polynomials. Okay, so this is a harder question. It sort of requires a bit more creative thinking. We have f of x we're told it's an odd function and that when you put -1 into the function, it will give a negative sort of output. So the y value will be negative. So we're told a possible graph showing y equals negative absolute value of x is which function? Okay, so the first thing we should note is that f of x is an odd function, which means that it will pass through the origin. Remember, odd functions have rotational symmetry, so therefore they always pass through the origin. And we're also told that when you put in a negative number, it's actually below the x-axis because it's negative. So it's going to give a negative output. So we don't know what it looks like, but we know it's going to sort of somewhat look like this, the original function. So it doesn't matter if it's like goes like that, as long as there's rotational symmetry going on. So for simplicity, I'm just going to sort of use a cubic sort of shape. Okay. So it's got rotational symmetry. It's negative when x is -1. Now, here's the thing. When I do y is equal to f of absolute value of x, then this will give me it's a shape that looks like a shape that looks like that, because I will disregard all the negative sort of things. I'm sorry, when I take the absolute value of x, so originally it looks like something like that. Everything that's positive, when x is positive, the absolute value of a positive thing stays the same. But when I sort of take the absolute value of x, all the negative x's become positive x's, so it'll be translating whatever is on the positive side of x, and it just gets flipped over. So if I change color, I will say this part gets ignored and you just get this part. So that's what it looks like for f of absolute value of x. But the next thing is we got a negative sign there. So when I put a negative in front of an x, that means it's reflected about the y-axis. So actually what happens is all of this will get sort of reflected Yep, so all of that will get reflected down, and sort of the only shape that looks like that is going to be C here. So C is going to be our answer. Yep, so just to reiterate what we did, we recognize since it's an odd function, it passes through the origin, and since f of -1 is negative, we know that it will sort of, when we're on the left side of the y-axis, it's below the x-axis, so it will look something like that. Afterwards, we took the absolute value, and then we recognized that meant that it we sort of reflected what was on the positive side across, but then because of the negative sign in front of the x, we're going to reflect everything about the y-axis, so it will end up looking something like that. So our answer is going to be C. Okay, so that was Year 11 content. We can move on to Year 12 content now. So we can look at mathematical induction, and I hope you appreciate all of these mathematical induction memes that I did. Yeah, with induction cooking and stuff like that. Okay. So we got this question. We remember from the syllabus you learn how to sort of identify errors and false proofs by induction. So here we're given this statement P of n, where we have sort of powers of 2 being added. And we have the statement that it's equal to 2 to the power of n minus 1. So there's this attempted proof by induction given below, and then they give it blah, blah, blah. And they conclude by the principle of induction the statement P of n is true. So we have to give 2 reasons why the given proof is incorrect and does not prove the statement. So I'm going to change back to red. So we can see they began by assuming the statement is true for n plus k plus, for n equals k plus 1. And then they're showing it's true for n equals k afterwards. So straight off the bat, we notice they've already skipped to the inductive element of the proof. Remember, mathematical induction has 2 important elements. You have to have a base element and also an inductive element as well. So the first error they made is they forgot the base case. They forgot to prove true for the first integer of the domain. So in this case, the first integer of the domain is n equals 1. So you need a base element, otherwise you don't actually prove anything by mathematical induction, because you need sort of a base element to set off a chain reaction to get the inductive logic to flow. Okay, so that's that. And secondly, we note that they assumed true for n equals k plus 1, and then they tried proving for true for n equals k using that assumption. So we can say, instead of proving true for n equals k plus 1, using assumption that n equals k is true, they did it the other way around. So that is your second error. They sort of messed up what you were supposed to assume to be true, and then using that assumption to prove the next thing. So here they swapped it around. You actually need to assume it's true for n equals k and then use that assumption to prove it's true for n equals k plus 1. So they did it the other way around. So those are your 2 errors, I would say, that you can quite easily spot in this proof. Okay, so this is a question now. We have to prove by induction that for all positive integers n, that n squared minus n minus 1 squared plus n minus 2 squared minus n minus 3 squared, all the way up to negative 1 to the power of n minus 1 times 1 squared is equal to n over 2 times n plus 1. So this looks a bit complicated, but just stop and ask yourself what sort of pattern this is. This thing at the end is just telling you the signs alternate between plus and minus, plus, minus, plus. Depending on whether n is odd or even, it will determine whether it's minus or plus, because remember, negative 1 to the power of an even number, it will be plus. If it's odd, it will be minus. So in other words, this is saying something like 4 squared minus 3 squared plus 2 squared minus 1 squared is equal to 4 over 2, 4 plus 1. And it's also saying, for example, 5 squared minus 4 squared plus 3 squared minus 2 squared plus 1 squared is equal to 5 over 2, 5 plus 1. Something like that. Notice how the signs alternate. The last term will depend on whether n is even or odd. So that's just a pattern. You're just taking your n, you're subtracting, you're squaring it, then you're going down consecutively and doing alternating minus, plus, minus, plus until you reach 1. Okay, so that's the pattern. Make sure you sort of understand what the pattern is before you sort of start diving into doing the proof. So our steps for induction are always the same, no matter what sort of mathematical induction question you're doing. So our first step is always to prove true for the first integer of the domain. So in this case, the first integer, we're told for all positive integers, n. So the first positive integer is 1. So we want to prove true for n equals 1. So we have 1 squared. We start with 1 squared and we go all the way up until it's 1 squared. But in this case, the last term is already 1 squared. So that's what we have on the left-hand side. And on the right-hand side, we have 1 over 2 times 1 plus 1, which is going to be half times 2, which is in fact 1. So that's also 1. So that's equal to the left-hand side. So therefore, we can say true for n equals 1. So we've proven our base element, it will be true for n equals 1. So now we can continue doing this inductive proof. So we will go towards step 2 now. So our second step is we want to assume true for n equals k, and we know k is a positive integer. Okay, so we assume that k squared minus k minus 1 squared plus k minus 2 squared minus k minus 3 squared all the way up to negative 1 to the power of k minus 1 squared is equal to k over 2 times k plus 1. So our third step is we want to prove true for n equals k plus 1. So what we're required to prove, so I'm writing an RTP for required to prove, is that k plus 1 squared minus k squared plus k minus 1 squared minus k minus 2 squared, etc., all the way up to negative 1 to the power of, instead of k minus 1, we'll have k 1 squared. And that's going to be k plus 1 over 2 times k plus 2. So that's what we're trying to prove. So how can we sort of deal with this? Well, the thing is, we notice that, oops, let me change color. We notice that we have a k squared and a k minus 1 squared and a k minus 2 squared, and all the way all of these terms are what we have in the assumption. The problem is they are opposite signs. We can see this is, instead of a k squared, we'll have a minus k squared. Instead of having a minus k minus 1 squared, we have a positive 1. So the signs are actually opposite. So, and even the last term here, k minus 1 squared, minus 1 to the power of k minus 1 is either positive or negative, depending on whether k is negative or even. It's negative, it's odd or even, but k being a consecutive integer afterwards, it's the opposite of whatever that will be. So if this one's negative, this will be positive, and if this one's positive, that will be negative. So all you need to recognize is that we already have all of these terms here. You just need to if we factorize out a negative from all of this, it will give us all of these terms, but with the right sign that we want. So we just need to factorize out a negative from it, and then we'll get this entire thing there. So I can say this will be, if I go back to the red, okay, this will be, the left-hand side is k plus 1 squared. So this is the unique new term, but all of these other terms will be here, except that the sign is different. So it will be the same thing as this, but it'll be the negative version of it. It'll be negative k over 2 times k plus 1. Because if you put a negative in front of all, if you multiply both of these sides with negative 1, you get negative k over 2 k plus 1 here, and here it will be negative k squared plus k minus 1 squared minus k minus 2 squared, etc. So then the signs will be right. So here, what I can do now is I notice both of these terms have a k plus 1. So I can actually factorize out, and notice I do want a 2, I do want a half at the front. So I'll factorize out a half k plus 1 from all of that. So here I'll get 2 times k plus 1 because I factorized out a half. So it will get a 2. And here, this I'm left with minus k times 1 because I already took out the k plus 1 and the half. So here, this will be half k plus 1. This will be 2k plus 2 minus k, and that's half k plus 1 times this will be k plus 2. And this will be k plus 1 over 2 times k plus 2, which is equal to what we want on the right-hand side. So we've proven that it's true for n equals k plus 1 if it's true for n equals k. So now we need to wrap up with our conclusion. So we can say if true for n equals k, it will be true for n equals k plus 1. And since it is true for n equals 1, which we did in part 1, in our first step, we've proven it was true for n equals 1, it will be true for n equals 2 and n equals 3 and so on for all integers, all positive integers. And that is how you do a question like that. So yeah, make sure you remember all of your steps. Do it methodically, go through it step by step, prove your base case, make your assumption, then use the assumption to prove that's true for n equals k plus 1, and then sum up with a conclusion. Alrighty, let's have a look at vectors now. So here's a question from the 2021 HSC paper. So this was 2 years ago. So we're given that the vector OP is negative 3, 1. So if we sort of negative 3, 1, sort of in this direction. So this is O and this is P. And that OQ is 2, 5. So it's sort of like that. It's not to scale, I'm just doing a rough sketch. So we're asked, what is PQ then? Well, we know that we want to find PQ. So we can say, using our knowledge of vector addition and subtraction, that PQ, I'll do it over here, PQ is equal to, it's going to be OQ minus OP. Because we can see if we do minus OP, it'll be here, and when we add that to OP, we'll get PQ. So it's actually going to be OQ minus OP. Or we can recognize that this is two vectors sort of with the tail together. So vector subtraction connecting the heads using head to tail is going to be this vector minus that vector. So in this case, OQ we said is 2, 5. And OP we say we know is negative 3, 1. So when we subtract, we'll do 2 minus 3, which is going to be 5. 5 minus 1, which is 4. So it's going to be 5, 4, which is our option C. And this makes sense. Out of these vectors, the only one that's pointing in this direction is 5, 4. The other ones, for example, 1, negative 6 will look something like that. Negative 1, 6 is going to look like that. And negative 5, negative 4 is going to look like that. So the only one pointing in this direction that we've got actually is going to be C. So we know C is our right answer. Okay, so let's do this question from the Norman Hurst trial paper now. So in this diagram, M is the midpoint of the line segment AB. And so we know that M here is the midpoint of AB. And vector ON is 4/5 of OM. So it is given that OA is A and OB is B. So they've labeled it for us here. OA is A, OB is B. So we're asked, which of the following expression correctly relates NM with A and B? So we need to find NM. So we're trying to find this vector here. Okay. So we know because we know ON is 4/5 of OM, this entire vector. This is in sort of, this is 4/5. So we know that the rest of the fifth must be NM. So since this is 4/5, this must be the other 1/5. So we can say from the start that we know that NM, which is what we're trying to find, is a fifth of OM. So it's a fifth of this entire vector here. So now we need to actually figure out what OM is. So we can say that OA plus AM, so we know that OM is going to be the sum of OA with AM. So if we sort of add this vector with that vector, we will get this vector here. And we know OA is by definition A. And now we just need to figure out what AM is. We know that AM is equal to, since M is the midpoint, it's going to be half of AB. So this is going to be A plus half of AB, like so. And to figure out what AB is, we know that when I add OA with AB, I'll get vector B. So I can say A plus vector AB is equal to B here. Using vector addition, A plus AB is equal to vector B. So therefore, AB must be equal to B minus A, like so. So therefore, OM is going to be A plus half times B minus A, which will give me A plus half B minus half A, which is equal to half A plus half B. So therefore, I can say OM is equal to half A plus B. Now, we've just found out what OM is, and we remember that NM is a fifth of OM. So therefore, we can conclude by saying that NM is equal to a fifth times half A plus B. So it must therefore be equal to a tenth of A plus B. And out of these options, that is going to be option C. So we can see our answer is C because NM is a tenth of A plus B. So just go through it sort of methodically. Look at what you're asked to find, which is NM. We recognize that's a fifth of OM, so we know we need to find what OM is. So then we just use our knowledge of vector addition and subtraction to figure out what OM is. We found out we needed AM, so then we just figured out it was half AB, and we can figure it out like so. Okay. So this is a sort of more tricky question. It's from the James Roos 2020 trial paper, and it sort of involves a bit of sort of creativity, I guess. So we're given a vector A, and we're told it is negative 3m. So it's represented by the ordered pair negative 3m. So in other words, it's the vector negative 3m, like so. And vector B is 4, 3, like so. So if the angle between vector A and vector B is an obtuse angle, which of the following is true for the value of m? All right, so so B is already fixed. We know B is going to be the vector 4, 3. So we can sketch that here with a diagram. So it's going to be 4, 3. So it's going to look something like that, maybe. Okay. So this is our vector B. And vector A, the horizontal x component is fixed. It's going to be negative 3. So if let's say this is the origin, so this is 4, 3, and it's fixed at negative 3. But m is variable, so the y value can differ. So if I sketch this on, I know that this is, let's say this is negative 3, and this is the origin, and this is 4. This is the line x equals negative 3. So we know that the vector can be on any part of this line because here the horizontal part is fixed. but the y value is not fixed. It could be any y value you want it to be. M determines the y value. The only thing we know that is fixed is the horizontal component of the vector. So it has to lie in the line x equals -3. So we know that the angle between A and B is obtuse. So the definition of an obtuse angle is that it must be between 90 degrees and 180 degrees. That is the definition of an obtuse angle. If it's 90 degrees, it's a right angle. If it's 180 degrees, it's a straight angle. It can't be less than 90 because that'll be acute, and greater than 180, it will be reflex. So it's between 90 and 180 degrees, we know. So the first thing is it needs to be greater than 90 degrees. So anything up, so if I go like really high up here, I will get an acute angle. So I want to see where it is equal to 90 degrees. So I want this to, let's say, what is the value of m that will give me a 90-degree angle? Because m can't be greater than that. If it's greater than that, it will give me an acute angle instead with this visualization I've drawn. So I want to find where it is equal to 90 degrees. So we know to get 90 degrees, the dot product of A and B must be equal to 0. So if I do the dot product of A and B, I can say the dot product will be -3 times 4 plus 3m is equal to 0. So I can say -12 plus 3m equals 0. So this will occur when 3m is equal to 12. In other words, when m is equal to 4. So m, if it's greater than 4, it will give me an acute angle. So m must be less than 4. So that's one condition we need, because anything less than 4 will avoid this situation of getting a right angle. And obviously you can't get another right angle when you go below because it's not possible. Anything like that, because of the fixation of our x being at -3. Okay, so it must be less than 4. That's one condition we have. But the thing is, it must be less than 180 degrees. So let's see what happens when it is equal to 180 degrees. It will be at this point here. Now, the thing is, if I go below it, is that a problem? Here, the thing is, if I go above 4, it's problematic because it'll give me an acute angle. But what happens if I go below the point where it's 180 degrees? If I go here, the thing is the angle will then be this angle here, and that is still obtuse, and that is fine. So the problem is, the thing is, we can have any value below 4, as long as it's not exactly equal to 180 degrees. So now we need to figure out what value will give us a right angle, a straight angle, a 180-degree angle. So because anything below that point is still fine, because you can you're still getting an obtuse angle, because the angle between A and B will still be obtuse there. So we can say that to find it when they're 180 degrees, we know B is for -3, so it will be parallel to the opposite, the negative vector of B. So when we put a negative sign on B, negative B will be -4, -3. So we know that to be 180 degrees, m must be a scalar multiple. So -3m will be a scalar multiple of -4, -3. So we can sort of say the ratios are the same. So we can say -3 over m must be equal to -4 over -3 to get them to be scalar multiples, to have the ratio the same. So we could say this will occur when we can say m over -3 will be 3 over 4. So this m will be equal to -9 over 4. So when m is equal to -9 over 4, it will be a 180-degree angle. So anything below that is fine because it will be obtuse. We just want to avoid having a 180-degree angle. Anything above it is also fine. It will be an obtuse angle. So therefore, our final condition is to avoid being an acute angle, we want it to be less than 4. And to avoid it being a straight angle, m can't be equal to -9/4. Because I kept the ratios the same as so when it's 180 degrees, the ratios of the vector will be the same as the ratio of the opposite vector of b, because they can't be parallel to each other. So therefore, our option is actually going to be option B. Our answer is B. So you can see this is why it's a level 3 sort of question. It sort of involves sort of some creativity, and sort of you can visualize and sort of understand your vector concepts in terms of the dot product and scalar multiples, and sort of understanding how you can sort of find what the condition of M must be. Okay, so this is from the 2021 HSC paper. For part 1, for vector v, show that the dot product of v with itself is the magnitude of v squared, and afterwards we're going to use it to prove a sort of geometric result. Okay, so for part 1, this should be a proof you should be very familiar with. You can do it 2 ways. We know with the dot product, when we have the dot product of a with b, it can either be the magnitude of a with magnitude of b times cos of the angle between them, or you can do the algebraic x1, x2 plus y1, y2. So here, let's say we do it the algebraic way, so we can let v be equal to xi plus yj. We know that the dot product of v with itself, therefore, is going to be x squared plus y squared, because it will be x1, x2, y1, y2. If it's with itself, it will be x times x plus y plus y. So you could write it as x times x plus y times y, which is x squared plus y squared. We also know that the magnitude of vector is the square root of x squared plus y squared. So therefore, we can say, if we square both sides, the square root of magnitude of v squared is therefore equal to x squared plus y squared, and therefore this is equal to the dot product of v with b as required. Okay, so that's one way you can do it. Another way is you could use the geometric formula. So we know that dot product of v with itself will be magnitude of v times magnitude of v times cosine of the angle between them. If it's the same vector, what's the angle between them? It's going to be 0. And we know from our cos graph that when cos is 0, it's equal to 1. So this is equal to magnitude of v times magnitude of v times 1, which is going to be magnitude of v squared as required. So both work. You can either use the algebraic formula, or you can use the geometric formula for the dot product. That will be fine. Okay, so let's go to part 2 now. So in the trapezium ABCD, BC is parallel to AD, and the magnitude of AC is equal to the magnitude of BD. So let AB, so this vector here, be, so I am going to actually clear all of this. Okay, so we'll do part 2 now. So let AB be equal to A, BC be equal to B, and this is a trapezium. BC is parallel to AD, so therefore AD is a scalar multiple of BC since they're parallel. So that's why we can write it as KBC. So KB, in other words, where K is positive, because it's longer than BC. So it's some scalar multiple of BC. And we also know that AC, the diagonal, the magnitude of that is equal to the magnitude of BD. So that's why we have these equals. They're equal in length. Okay. So they're like using part 1 or otherwise, show that 2 times the dot product of A with B plus 1 minus K times magnitude of B squared is equal to 0. Okay. So for part 2, we recognize that the dot product of a vector with itself is equal to the magnitude of the vector squared. So here we know that AC magnitude is equal to magnitude of BD. So a good starting point here would be to find what AC is in terms of A and B, and also to express what BD is in terms of A and B as well. So we can say AC is the vector A plus B. And we can also say that BD is going to be what we get when we do KB minus A. So if you do minus A plus AD, so when we do, like if I change color here, if I do minus A plus AD here, I'll get BD. So it will be KB minus A. Okay. So now I can say that since the magnitude of AC is, we know the magnitude of AC is equal to the magnitude of BD. So I can do that here. I'll say that we know that magnitude of AC is equal to magnitude of BD. So therefore, the magnitude squared must be equal to the magnitude of BD squared. So I took the thing that we given, that the magnitudes are equal, and since they're equal, I can square both sides. Now, we know that when we have the magnitude squared, it's equal to the dot product of that vector of itself. So therefore, I can say the dot product of AC must equal the dot product of BD with itself. And from my earlier working, I know AC is A plus B and BD is KB minus A. So I can say here that this means we're doing the dot product of A plus B with itself, and that's equal to KB minus A, and doing the dot product of that with itself. Okay, so I can now expand using my laws of the dot product. Remember, it sort of like follows the rules of normal multiplication. There's the commutative law, the distributive law, and the associative law. So here, this will be, I can sort of treat it like normal bracket expansion, but with the dot product. So I can say dot product of A with itself, plus dot product of A with B, plus dot product of B with A, plus dot product of B with B is equal to here. K is a constant, so this will be K squared times dot product of B with B. This will be minus KA dot product with B. Or you can do KB dot product with A. Then minus KA dot product of B plus dot product of A with A, like so. So here, dot product of A with itself will be magnitude of A squared. Here we did, using the commutative law, we know dot product of A with B is the same thing as dot product of B with A. So this will be plus 2 dot product of A with B plus magnitude of B squared. Here, I will say I will have a K squared. Dot product of B with B is B magnitude of B squared. Here I have two of those, so it will be minus 2K. Dot product of B with A is the same thing as dot product of A with B, so minus 2A dot product of A and B. And remember, of the associative law allows us to sort of take constants around and move them around. So it doesn't matter if it's K times dot product of B with A or whether it was K B times dot product of A. It's the same thing using the associative law of the dot product. Plus magnitude of A squared. So this cancels out with that nicely. And now what I can say is we look at this result we want at the end. So we already have this 2 times dot product of A with B already here. So I can what I can do is I can sort of take everything to one side. So I'll say that 2 dot product of A with B plus magnitude of B squared minus K squared magnitude of B squared plus 2K A dot product of B is equal to 0. So that's not exactly the same as here, so we need to keep working algebraically. So what I can recognize is I can factorize out a 2 dot product of A with B here. And here I'll have 1, and here this will be plus K. And from here, I can factorize out a magnitude of B squared. So this will be plus magnitude of B squared times 1 minus K squared is equal to 0. So I have this result now, like so. And the thing I need to recognize is this thing here is the difference of 2 squares. So I can actually simplify that and say this is going to be 2 dot product of A with B times 1 plus K plus magnitude of B squared times 1 minus K times 1 plus K. And that's equal to 0. Now we notice that these two terms have a 1 plus K. And the thing we recognize from the question is K is greater than 0. So that means for 1 plus K must be greater than 1, which means it can never be 0. So that means we can divide by 1 plus K without any problems, because normally you can't divide by polynomials because there's a possibility it might be 0 and we can't divide by 0. But since 1 plus K is greater than 1, we can note that we can divide by 1 plus K. So I can divide everything by 1 plus K. 0 divided by 1 plus K is still 0. So I can therefore say 2 times dot product of A with B. I have this 1 minus K already here, plus 1 minus K times the magnitude of B squared. That is equal to 0 as required. And therefore, we are done with this geometric proof. We've shown that 2 times the dot product of A with B plus 1 minus K times the magnitude of B squared must be equal to 0 as required. And that is how you do this real HSC question that came up in the 2021 paper. Okay, so we can go on to this question now. So this is actually a projectile motion question from the Borkham Hills 2022 trial paper. So here we have a particle and it's projected with an initial velocity v meters per second at an angle theta to the horizontal from a point O on the edge of a vertical cliff 32 meters above a horizontal beach. So the thing is, this is the point O. This is where our origin is. So it's 32 meters above the beach. The particle moves in a vertical plane under gravity, and its position vector r of t is given by this vector. So they've given us the position vector of the projectile. And we don't need to prove it, they gave it to us. The particle hits the beach after 4 seconds, 64 meters from the foot of the cliff. So we know after 4 seconds, it will land all the way here, and this is 64 meters away from the foot of the cliff. So for part 1, we're asked to find the exact value of v and find the value of theta to the nearest degree. So the thing is, this here is going to be, since this is the origin, this vector here in its final position after 4 seconds is actually going to be the vector 64, negative 32. So remember, the origin is here, so this is actually 32 meters below the origin, so it's negative 32, and this is 64 meters to the right. So I can therefore say, for part 1, to find the exact value of v and the value of theta, I can say when r is 4, this will be equal to this vector here. When I put that in, this will be, here it will be v times 4 cos theta, and this will be v times 4 sine theta minus 5 times 4 squared. And this is equal to the vector, because this is the position vector. The position vector after 4 seconds is 64, negative 32. So I can therefore say I can equate the x values and the y values together. I can therefore say that 4v cos theta is equal to 64. So therefore I can say v cos theta is equal to 64 divided by 4, which is going to be 16. And for second part, I can therefore say that 4v sine theta minus 5 times 4 squared minus 80 is equal to negative 32. So I can say that 4v sine theta is equal to 48. So therefore v sine theta must be equal to 12. So I have these two equations now. So I can go ahead and start solving to find what v and theta are. So to find what v is, I'm going to, this is similar to the auxiliary angle method. You can sort of square equation 1 and add it with the square of equation 2. So I can say v squared cos squared theta plus v squared sine squared theta is equal to 16 squared plus 12 squared. So I can then factorize out v squared from both of these terms. And this will be 16 squared. This will be 256 plus 144. So I might go back to here because I'm running out of space. I can say that v squared cos squared plus sine squared is equal to 1. And that's equal to 256 plus 144, which is going to be 400. So therefore v must be the square root of that, which is going to be 20. And we know v is positive, so we don't need to do plus minus 20. So we know v is going to be 20 meters per second. That was our initial velocity of this particle. And to find theta, I can do equation 2 divided by equation 1. So 2 divided by 1. So 2 we said is v sine theta. And divided by 1, which is v cos theta, is going to be 12 over 16. So therefore, the v's will cancel out. So I can say sine theta over cos theta, which becomes tan theta. That is 12 divided by 16, which is 3 over 4. So therefore, I know that theta must be equal to, and make sure your calculator is in degrees because I want it to the nearest degree. When you do inverse tan 3 over 4, that's going to be 37 degrees to the nearest degree. So therefore, we got our answer. V is 20 meters per second. Theta is 37 degrees. And that is how you answer part 1. We found the exact value of V and the value of theta as well. Okay, so for part 2, they're like, find the speed of impact with the beach, correct to the nearest meters per second, and the angle of impact with the beach, correct to the nearest degree. So we want to find the impact velocity and the impact angle. So we are told what the position vector is, which we said is bt cos theta, bt sine theta minus 5t squared. So in order to find angle and velocity, we actually need the velocity vector. So what I can do is I can differentiate this vector. I can say the velocity vector is therefore equal to, I will differentiate everything with respect to time. The derivative of vt cos theta will just be v cos theta. And the velocity of the vertical velocity will, the derivative of the vertical aspect is going to be v sine theta and this will be minus 10t, because I'll take the 2 to the front, and it'll become minus 10t. So this is my velocity vector. So I want to find what the velocity vector is once it lands, and that happens 4 seconds after the launch. So the velocity vector when it hits the ground will be equal to, and the thing is, from our earlier work, we know that tan theta equals 3 over 4. So we know tan theta is equal to 3 over 4. So if I draw a little triangle, opposite over adjacent is tan. So therefore, using Pythagoras, this other side must be 5. So cos theta is going to be, B we said is 20, by the way, from part 1. So this will be 20 times cos theta, which we say is 4 over 5 because it's adjacent over hypotenuse. The sine theta is going to be 20 times 3 over 5 minus 10 times t, which is 4. So our velocity vector when it hits the ground is actually going to be 16, and here we'll have 20 times 3 over 5 minus 10 times 4, which is minus 28. So we know it's going to look something like this. It'll be traveling downwards. The vertical component is 16. The horizontal component is 16. The vertical component is negative 28. So that's why it's going down like that. So the actual speed when it hits the ground is the magnitude of the velocity vector. So the speed of impact is the magnitude of this. So this will be root 16 squared plus negative 28 squared. That's going to be, if I do that, actually going to be 32. They want it to the nearest meters per second. So it'll be 32.249, which is 32 meters per second. Nearest meter per second. So it'll be 32 meters per second, it'll hit the ground. And to find the impact angle, we can just use this triangle here. So the length of this triangle, even though it's going down, will be negative 28. The length is still 28. So this angle here, tan theta, well, we'll call it alpha since we already used theta. So tan alpha is going to be opposite, which is 28, over adjacent, which is 16. So alpha is going to be 28 over 16. So inverse tan 28 over 16, which will be 60.25. So which is 60.25, which is 60 degrees to the nearest degree. But you need to specify where you're taking it. So we've taken the velocity at this point, it's 16 here. It's traveling downwards at 28, negative 28. So therefore, the angle here we've drawn is this angle here. That's alpha. So it'll be 60 degrees below horizontal. You need to specify that. Otherwise, you could have written 120 degrees with the positive ground or something like that. But if you taking it below the horizontal, you specify the angle that it impacts the beach is 60 degrees below horizontal. So you need to specify that. Otherwise, you could lose marks. So yeah, it hits the ground at a speed of 32 meters per second at an angle of 60 degrees below the horizontal. Okay, and that's how you do a question like that. Remember, when you're looking at sort of speed and also angle, make sure you're working with the velocity equation. So here we had to differentiate the position vector to get our velocity vector. Okay, so that was vectors. Now we can move on to trigonometry. So let's start off with this multiple choice question from the 2021 HSC paper. So we're asked which curve best represents the graph of the function f of x equals negative a sine x plus b cos x, given that the constants a and b are both positive. So we can have a look at the graph, and we can note that, first of all, let's just an easy way to sort of rule out sort of answers through the process of elimination is just plug in 0 to see where the y-intercept is. So if we put f of 0, so we're told a and b are both positive. So we have negative a sine 0 plus b cos 0. So we know the value of sine 0 is 0, so this will be 0. And cos 0 is 1, so this will be plus b. So this will be b, and b is a positive number, so it will be the y-intercept is actually going to be positive. So therefore, we can rule out a because that has a negative y-intercept, and also c because it has a negative y-intercept. So we're just between b and d now. So what can we do? There's multiple ways you can go about doing this. The way I like to do it, the way I did this question, is I then differentiate it. So I differentiate it to find what the derivative is. So this will be, in this case, minus a cos x, and the derivative of cos x is negative sine x. So let me just write it somewhere else. I differentiate it. It's going to be minus a cos x, and since the derivative of cos x is negative sine x, it will be minus b sine x. So now I want to see what the rate of change is, what the gradient of the tangent is when at the y-intercept, so at when x equals 0. So I'll put in 0 into the derivative, so this will be negative a cos 0 minus b sine 0. So we know that cos 0 is 1, so this will be negative a, and sine 0 is equal to 0, so this will be just 0. So it will just be negative a, which is less than 0 because a is positive. So therefore, I know at the y-intercept, it must be decreasing. So here with this one, at the y-intercept, it's increasing. The gradient is positive of the tangent, but here it's decreasing. So the right answer must be D, because the derivative at x equals 0 is negative. And also it has a positive y-intercept as well. So the correct answer must be D. So that's how I did that question. You could find your own way to do it. There's multiple ways you could approach this question. Okay, so this is from last year's HSC paper. And this is testing our knowledge of the auxiliary angle method. So we need to convert root 3 sine x minus 3 cos x into the form r sine x plus alpha. Now, the tricky part of this question is they've prescribed a form for us to use. Normally, we could pick any form. We could pick r sine, and since we notice this is negative, we would pick x minus alpha because we want to match the sign to make easy working. But the problem is they want us to do plus alpha instead. So that's a tricky part of this question. It's possible, but we need to consider quadrants now instead of just having acute angles to work with. So we'll start off by letting root 3 sine x minus 3 cos x being identically equal to r sine x plus alpha, like so. So I'm going to expand this using the compound angle formula. So I know that r sine times x plus, r sine x plus alpha is going to be, when I expand this, r sine x cos alpha plus r cos x sine alpha, like so. Because with sine, when you expand it, the signs are the same. So now I can compare coefficients. Coefficient, like so. So I'm going to change color to illustrate this. So the coefficient of sine x on the left-hand side is root 3, and the coefficient of sine x on the right-hand side is r cos alpha. And here, the coefficient of cos x is r sine alpha, and here the coefficient of cos x is negative 3. So therefore, I can say that r cos alpha is equal to root 3, and r sine alpha is equal to negative 3. So I need to find what r is. So I can square both of these equations and add them together. R squared sine squared alpha, that's going to be 3 plus 9, because the square root of, so the square of root 3 is 3 and the square of negative 3 is 9. So this will be R squared cos squared alpha plus sine squared alpha. That's equal to 12. So R squared times 1 is equal to 12. So R is therefore equal to root 12 because R is positive, and that's equal to, it's going to be 2 root 3. Like so. So we know what R is now. So we have to find what alpha is. So what I can do is I can divide equation 2 with equation 1. So I can say R sine alpha over R cos alpha is equal to negative 3 over root 3, which is equal to, R's cancel. This will be tan alpha. And negative 3 over root 3, if I rationalize, is equal to negative 3 root 3 over 3, which is equal to just negative root 3. So now we have the problem of figuring out which quadrant we're in. We know tan is negative. So since R is 2 root 3, R is positive, we know cos is positive. We know sine is negative. So sine is negative because R is positive. If you take that to the other side, that's going to be a negative number. So which quadrant are we in that cos is positive, sine is negative, and tan is also negative? That must be the fourth quadrant. Because tan is positive, cos is positive in the fourth quadrant, sine is negative, tan is also negative in the fourth quadrant. So we know we are in the fourth quadrant. So our reference angle that we associate with root 3 and tan is going to be pi on 3. So if we're in the fourth quadrant and this is pi on 3, our angle must therefore be 5 pi on 3. And hence, because that's a fourth quadrant angle, that's a fourth quadrant angle that gives us negative root 3 for tan and also gives us sort of a positive cos and a negative sine result. A positive, that gives us a positive cos and a negative sine. So therefore, we can say, if I change color, that therefore, negative 3 sine x minus 3 cos x is identically equal to 2 root 3 sine x plus 5 pi on 3. And that is our answer for how we sort of write this in the form r sine x plus alpha. Okay, so we can move on to the next question now, which is from the 2022 Morgan Hills High School trial paper. So we're given that the angle theta satisfies this equation. So we know that theta is an angle which makes that this is true. So we know that in this case, sine 2 theta plus pi and 4 is equal to 3 cos 2 theta plus pi and 4. And for part 1, we have to show that tan 2 theta equals half. And then for part 2, we need to hence insert form, find the exact value of tan theta, given that theta is an obtuse angle. Okay, so for part 1, we need to show that tan 2 theta is equal to half. So, all right, let's go. So we can say, so we know that sine 2 theta plus pi on 4 is equal to 3 cos 2 theta plus pi on 4. So we notice that both of these things inside the sine and cos are both 2 theta plus pi on 4. So what I can do is I can divide both sides with cos 2 theta plus pi on 4. Now, here's the thing. Sine 2 theta plus pi on 4 over cos 2 theta plus pi on 4 will become tan 2 theta plus pi on 4. And this thing will just become 3. This will cancel with that. So it's just 3. So now we need to figure out a term for tan 2 theta. So I have a tan of 2 angles being added together. So I can use the compound angle formula for this. So I can say over here that tan 2 theta plus tan pi over 4 over 1 minus tan 2 theta tan pi on 4 is equal to 3, using my knowledge of the compound angle formula. So tan pi on 4 is equal to 1. So I can say tan 2 theta plus 1 over 1 minus, this is tan 2 theta times 1, is equal to 3. So I can now take that to the other side. So I can say tan 2 theta plus 1 is equal to 3 minus 3 tan 2 theta. So I can take that to the other side. So this will be 4 tan 2 theta is equal to 3 minus 1, which is 2. So therefore, tan 2 theta must be equal to 2 over 4, which is equal to half as required. So we are done with that. We've successfully proven that tan 2 theta is equal to half. Since it satisfies that equation, therefore tan 2 theta must be equal to half. Okay, so they're like for part 2, hence find in third form the exact value of tan theta given that theta is an obtuse angle. So we know that tan 2 theta is equal to half. So we need to find in third form the exact value of tan theta. Okay, so tan 2 theta is equal to half. So we can say that this, using the double angle formula, tan theta, so we can, this will be 2 tan theta over 1 minus tan squared theta is equal to half. So I can just let t be equal to tan theta to make it easier for myself. So this is 2t over 1 minus t squared, and that's equal to half. So I can therefore say 4t is equal to 1 minus t squared. Yeah. 4t is equal to 1 minus t squared. So therefore, if I take it here, t squared plus 4t, you can either use the quadratic formula or you can complete the square. So I'm going to go with completing the square, I guess, here. So t squared plus 4t, so if I took that to the other side, is equal to 1. So t squared plus 4t is equal to 1. So I can say t squared plus 4t plus 4 is equal to 5. I added 4 to both sides. So here this will be t plus 2 whole thing squared is equal to 5. So t plus 2 is equal to plus minus root 5. So t is equal to negative 2 plus minus root 5. But theta is an obtuse angle. So we can say, so this is tan theta is equal to minus 2 plus minus root 5. But theta is an obtuse angle. And what quadrant does that mean we're in? Obtuse angles are between 90 degrees and 180 degrees. So that's the second quadrant. So in the second quadrant, remember all stations to central. In the second quadrant, tan is negative. So therefore, tan theta must be negative. So therefore, tan theta must be the negative case. It must be negative 2 minus root 5, since theta is obtuse. So yeah, in this case, you could have used the quadratic formula to solve this quadratic. I just used completing the square because I found it was an easy case to complete the square here. So yeah, just in this case, you just had to use the double angle formula for tan to solve for tan theta. And I just let t be equal to tan theta. So it's sort of a t formula question as well. Alrighty, so that is trig. We can move now onto our calculus content. Okay, so this is from the James Roos trial paper. So we're asked which of the following differential equations yields the direction field below. So we have this direction field, and we're asked to find which one it could be. So this is sort of a harder one because there's sort of some areas, there's sort of also some creative thinking you need to sort of apply to this question. Okay, so something I noticed straight away is that at the y-intercept, when x is equal to 0, they're all horizontal slopes. So we know that when x equals 0, the derivative must be equal to 0. So here, when x is in the bottom, you can't divide by 0. Here at the y-intercept, that's when x is equal to 0. So when you divide by 0, that's undefined. So you end up with an undefined gradient, which is a vertical line instead, which isn't the case here because we have horizontal lines. So we can actually rule out b and d already, because that's not the case at the y-intercept. And here, a and c both work, because when you plug in 0 in the top, it becomes 0. It makes a whole big 0. So we know it's either going to be a or c. So now, the next thing we need to consider is sort of the fact that we have cos and sine here. So the difference is one is cos x plus y, the other one is sine x plus y. So if we take a look at this case, when we have, let's just look at any features we can recognize. Let's see, we take a look at this line here. All of the gradients are the same. It looks like they're all -1. If I highlight this segment here, you can see all of the gradients here are the same. They all seem to be -1. So this is occurring when y is equal to -x. This is at the line y equals -x. So when y is equal to -x, we know that if y is equal to -x, x plus y must be equal to 0. And the thing is, when we have y being equal to -x, if we do x over y, since y is equal to -x, that's going to be x over -x, which is -1, which matches this thing here. The gradients are all -1. If it's just, if we just consider the x over y. Now, the problem is, when y is equal to -x, x plus y must be equal to 0. Now, if this was sine, this would be x over y is equal to -x, sine 0. And this entire thing will be 0. So if it was in fact 0, at this segment where y is equal to -x, you would expect horizontal flat lines because sine 0 is 0. But the problem is we still have these -1 things. So instead, if we have cos 0, we know that cos 0 is equal to 1. So when y is equal to -x, here we'll get x cos 0 over y, which is -x, which will be -1, because cos 0 is just 1. So therefore, that actually works out to be a then, because at this line, at y equals -x, x plus y is 0, cos 0 is 1, x over y will be -1. So therefore, our answer is going to be A. So you have to sort of look at the features of the graph. The key features I took away with this graph is looking at the y-intercept, the y-axis, that eliminated two of our solutions, and then looking at this segment where y is equal to negative x, noting that cos 0 is equal to 1, and that x over 1y, when y is equal to negative x, it will just be negative 1. So yeah, it's sort of a tricky question, but yeah, a really sort of fun question once you figure out how to do it. Okay, so this is from the Sydney Grammar Trial paper. Solve the separable differential equation dy dx equals x times y squared plus 4 if the solution passes through the point 0, 2. And we're told to express your solution as a function of x. So we need to make y the subject in this case. So, all right, let's do it. So we know that dy dx is equal to x times y squared plus 4. So to separate the variables, we need to make sure all the x's and all the y's are the same, on the same side before we can actually go and integrate it. So we're going to separate the variables. So I can take the y's to the other side. So dy over y squared plus 4 is equal to x dx, like so. So I took the dx to the other side. I treated it like a fraction. I took the dx to the other side. I took the y's to the other side. So now I can say the integral of 1 over y squared plus 4 is dy is equal to the integral of x dx. So how do I integrate 1 over y squared plus 4? Well, the thing is, I can recognize this is in the form 1 over a squared plus y squared, because this is going to be 2 squared plus y squared. And before I can integrate this, remember the form is a over a squared plus x squared. In order to, when you integrate this, this will give me inverse tan x over a. So, oh yeah, plus c. So, in this case, I will so this is 2 squared. I will put a 2, but also divide by 2 on the outside to balance out the fact that I am adding a 2 here. So now this will give me half inverse tan x over 2. And this is like, we can say, oh, sorry, not, this is y over 2, because this is all in terms of y. So, yep, half inverse tan y over 2 is equal to x squared over 2. And don't forget your plus c. And it doesn't matter which side you put the c on, as long as you have the c. So we can say, also, c can be anything. So I could say this is plus c over 2. The reason why I do c plus 2, c is as long as you have some constant, because I notice everything is divided by 2. So now I can multiply everything with 2. So inverse tan y over 2 is equal to x squared plus c. So now I can figure out what c is. So when x is equal to 0, y is equal to 2. So therefore inverse tan 2 over 2, which is 1, is equal to 0 plus c. So that's pi on 4, which is c. So therefore c is equal to pi on 4. So inverse tan y over 2 is equal to x squared plus pi on 4. So therefore I can say y over 2 is equal to tan x squared plus pi on 4. So therefore my final answer is that y is equal to 2 tan x squared plus pi on 4. And that is my final answer for expressing the solution as a function of x. Y is going to be equal to 2 tan x squared plus pi on 4. So yeah, you can see the steps with doing this. You separated the variables first. So I put all the x's and y's on one side. So I took the y squared plus 4 to the other side, and I took the dx to the other side. I then integrated both sides. I recognized this was a standard integral that will give me inverse tan. So I manipulated it to get me into that form. So this will give me half inverse tan y over 2. And this will be x squared over 2 when I integrate. And then I kept solving. I found what c was. And then I I rearranged and made y the subject. So now I know y is equal to 2 tan x squared plus pi on 4. Alrighty. So this is a question from the Sydney Boys 2022 trial paper. So we have the graph of y equals ln x. And the region bounded by this region and the line x equals 4 and the x-axis is rotated around the y-axis to form a solid. So now we need to find the volume of the solid. So it will will have this sort of shape, and there'll be like sort of a hole here. So it will look something like this. Now the thing is, you need to actually have this graph and sort of sketch what the volume looks like to avoid making silly mistakes. People could just blindly apply the formula that volume is equal to pi integral from a to b. In this case, we're rotating around the y-axis, so x squared dy. That will not get you the right answer in this case because you actually need to see what's going on. So we are trying to get the volume of this solid here. So we notice that if we just apply the formula from 0 to 1 to ln over 4, what we're actually getting is, if I change the color, it's actually going to be this volume here that we'll get with the formula. Because the x value of this point, when you take the radius for a slice, it's actually going to correspond to this green volume here when you do pi x squared dy. So this actually gives you the area of the hole. So what we can say is that this, if I clear up, sorry. So what we actually want to find is our volume is going to be, we actually notice there's a cylinder here that we get when we rotate x equals 4. Like, so, yep, this is a cylinder over there. And we want to subtract the hole, which is going to be sort of this funnel looking shape. And when we subtract the hole from this cylinder, we actually get the real volume we're trying to find. So we need to do that. We need to find what the volume of the cylinder is. So if I sort of sketch that again. So we have this sort of cylinder. The radius of the cylinder is 4. Because this is 4. And the height of the cylinder is, this is ln 4. So it will be ln 4. So the volume of the cylinder that we have here, because this is 4 and this is ln 4, is going to be pi 4 squared times the height, which is ln 4. So this will be 16. So that's the cylinder volume. And then we're going to subtract the whole volume, which is going to be our application of the formula, pi integral from 0 to ln 4 x squared dy. Because here, this is a point, like this could be any point on the function. The radius of this slice here is going to be x. So when we slice all the way from 0 to ln 4, we'll get the volume of the whole. So in this case, that's how we're going to establish how we're going to find the volume. So we can say this is going to be 16 pi ln 4 minus pi integral from 0 to ln 4. Now I need to, this is x squared dy, so I need to make x in terms of y. So I know that y is ln x. So therefore I can say that e to the power of y is equal to x. So therefore x squared must be equal to e to the power of 2y. Okay, so this will be x squared is e to the power of 2y. And we've got dy. So this is a function with a function inside. The derivative of 2y is 2. So I need to make sure I have a 2 on the outside before I can multiply. before I can integrate. So this will be 16 pi ln 4 minus pi on 2 from 0 to ln 4 to e to the power of 2y. So this is in the reverse chain rule form now. The derivative of e to the power of 2y, which is the derivative of 2y, which is 2, is on the outside. So now I can just integrate this entire thing directly. So this will give me, in terms of my volume, this will be equal to 16 pi ln 4 minus pi on 2. This will be e to the power of 2y from 0 to ln 4. So this will be 16 pi ln 4 minus pi on 2. This will be e to the power of 2 ln 4 minus e to the power of 0. So 2 ln 4 is the same thing as ln, I can take that inside the logarithm, so this will be ln 16. So e to the power of ln 16 will just become 16. So this will be 16 pi ln 4 minus pi over 2, 16 minus 1. So this will be 16 pi ln 4 minus 15 over 2 pi. And yeah, you could leave it like that, or you can just factorize out a pi. So this will be 16 ln 4 minus 15 over 2 pi. And that is your volume of this solid of revolution. It's going to be 16 ln 4 minus 15 over 2 pi. I'll just write it again here in case my sort of camera the video is blocking it. The final answer is 16 ln 4 minus 15 over 2 pi, like so. And you can write cubic units because it's going to be a volume. Okay, so that is our answer for that question. So now we can move on to our very last topic from the syllabus, which is statistical analysis. So this is from the James Roos paper from 2020. So we have a random variable. It's defined by the probability of getting exactly k for that random variable is given using this formula. For k is from 0 to 15. So we're asked, what is the mean of this random variable? Well, we know if the exact probability of getting k is this is the binomial probability formula. So that means we know k is a binomial, we know x is a binomial random variable. So how many trials do we have? Well, we have 15 of them because we're choosing how many successes from the number of trials. So that's going to be 15. So we know that our number of trials for the binomial random variable is 15. So now we also need to know the probability of success. Well, if we want exactly k successes, here we're multiplying we're raising 0.29 to the power of k. So we know we want exactly k successes. That means our probability of success is 0.29 in this case. So we know n is 15 and our probability of success is 0.29. And we're asked to find the mean of x. So to find the mean, so that's the expected value of x, that's going to be NP. So that's going to be 15 times 0.29. And if you do that, we know that the mean is going to be 4.35. So therefore, our answer for this question is going to be C. That is our mean of x. Okay, so here's a question from last year's trial paper from Balcombe Hills. So at a cafe, customers ordering hot drinks order either tea or coffee. Of all the customers, 20% order tea and 80% order coffee. Of those who order tea, 60% take sugar, and of those who order coffee, 35% take sugar. So for part 1 of this question, we have a randomly selected customer who orders a hot drink and they're chosen. We need to show that the probability that the customer takes sugar is 0.4. Okay, so let's do part 1. So in order to we're trying to find a probability that that customer takes sugar. So you can either be a person who has tea and takes sugar, or you can be a person who has coffee and takes sugar. So to be a person who has who sort of takes tea and takes sugar, first of all, you need to take tea. So the probability of that occurring is going to be 0.2. And you take tea and you take sugar. So 60% of those who take sugar, 60% of those who take tea take sugar. So if you are a person, the probability of selecting a person who takes sugar because they take tea is 0.2 times 0.6. But we're not concerned with whether or not they take tea or coffee. We're just concerned with whether or not they take sugar. So the other situation is they take coffee and take sugar with their coffee. So it's or they take coffee and sugar. So if with or, we need to add it together. So here it's and, so we multiply. So this is tea and sugar, or there can be coffee and sugar. So to order coffee, the chance of that happening is 0.8. And if out of those who order coffee, 0.35. So 35% take sugar. So if we do that, the probability that we take sugar is you either have tea and sugar or coffee and sugar. So here, that will be 0.2 times 0.6, which is 0.12, plus 0.8 times 0.35, which is 0.28. So that will be, when you add it together, 0.4 as required. So we know that 40% of the customers take sugar, basically. They can either be a person who orders tea and takes sugar, or a person who orders coffee and takes sugar. But we're just concerned with them taking sugar. So 40% take sugar, 60% don't. So for part 2, we have a random sample of 10 customers ordering hot drinks. Find the probability that exactly 4 of the customers take sugar. Give your answer correct to 4 decimal places. Well, here we have a binomial sort of experiment now. So each person taking sugar or not, that's considered a Bernoulli trial. And we have 10 trials happening, and they're independent of each other. So we've got 10 trials. The probability of success of getting someone who takes sugar is 0.4. So here, so this is, we can let X be number of people taking sugar. So here, we're concerned with the probability that X is exactly equal to 4. So we're going to account for how many ways we can choose 10 of those people from the sample. Choose 4 of the people from our sample out of the 10 people we have to take sugar. We want exactly 4 to be with sugar, and we want 6 to be without sugar. So the chance of them not taking sugar is 0.6, and we want 6 of them without taking sugar. So if we do that, that's going to be 10 choose 4 times 0.4 to the power 4 times 0.6 to the power 6. That's going to be 0.250822. So to 4 decimal places, that's going to be 0.2508. So around like a quarter chance, around 25%. So 0.2508 is our probability that exactly 4 of the customers take sugar. Okay, so that's how we do part 1 and 2. So now we can go to part 3. So use the extract shown from a table giving the Z table, so the values that Z is less than Z. So this is the sort of Z table that tells us the values of the cumulative distribution function of the standard normal distribution. Z has a standard normal distribution to estimate the probability that from a sample of 150 customers ordering hot drinks, at least half of them take sugar. Okay. So here we can either use a normal approximation with counts, or we can use a normal approximation. So we can just keep it with X in terms of the number, or we can just use the sample proportion. So here I'm going to use sample proportion. So our sample proportion, so we know here that X is binomially distributed. And we have a sample of 150 customers now. So we're not doing the 10 customers with the exact probability. We have a large sample now of 150. So the larger the sample, the better our normal approximation is. So we have 150 people, and our chance of getting sugar is still 0.4. So X being the number of people from the sample who take sugar. Okay, so the mean is going to be 150 times 0.4. So, yep, this is our mean, our expected value. So that's going to be 150 times 0.4, which is 60. And our standard deviation is going to be the square root of NP times 1 minus P, which is square root of 150 times 0.4 times 0.6. So that's the square root of 36. So the standard deviation here is 6. So you can use this and you can just find what half is. So 150, half of 150 is going to be 75. So you could use 75 for your standard normal distribution approximation. But I'm going to use the sample proportion here. So the expected value of the sample proportion, the mean, is going to be 60 divided by n, which is 150. Because I already found what the mean was. So that's going to be 0.4. So it makes sense. You expect your sample proportion to be similar to the probability of success. So I need to find the standard deviation of the sample proportion now. So I'll just take the standard deviation that I found and divide that by n. So in this case, that will be 6 divided by 150, which is 0.04. So now I'm trying to estimate the probability that at least half of them take sugar. So the sample proportion being greater or equal to half. Because I want at least half of them taking sugar. And remember, the sample proportion is the proportion of successes that are, the proportion of trials that are successes. So this is approximately the same as the probability that Z is greater than, remember Z is a continuous random variable, so it doesn't matter if you have greater or equal signs because the probability of it being exactly something is 0. So Z is greater than, or you can, it doesn't matter, we can, the probability that Z is greater or equal to 0.5 half minus the mean. I'm going to standardize 0.5. So 0.5 minus the mean, which is 0.4, divided by this standard deviation, which is 0.04, which is approximately that Z is greater or equal to, if I do 0.5 by 0.4, 0.04. The Z score of that is 2.5. So I need to figure out, if I have a standard normal distribution, if this is 2.5, I need to find the area of that to the right of 0.5. So this will get, to find this, remember this table gives me the area to the left of that Z score. It's cumulative. So to find the area to the right, the area under the entire curve is equal to 1. So this will be 1 minus the probability that Z is less than 2.5. So I'll just find the area to the left of 2.5 and subtract it from 1. So doing that, if I move my work in here, that is going to be equal to, on the table, 2.5 is 0.9938. So this is 1 minus 0.9938. So therefore, my answer is, so this is a separate line of working. Yeah, so my answer is going to be, on the table, 2.5 is 0.9938, 1 minus 0.9938. It's going to be 0.062. So if you want, you can write it as a percentage, which is 0.62%. So you have less than a 1% chance that if you sample 150 people, that at least half of them take sugar, because your chance of getting someone who takes sugar is only 0.4. So your probability that at least half of them taking sugar, if you take a sample of 150, is actually going to be like less than 1%, 0.62%. So that's how you do a question like that. Okay, this is our last question we'll go to before we go over tips for the HSC. So this is actually from last year's paper. So we have a game, and it consists of randomly selecting 4 balls from a bag. After each ball is selected, it is replaced in the bag. So the bag contains 3 red balls and 7 green balls. For each red ball selected, 10 points are earned, and for each green ball, 5 points are deducted. For example, if a player picks 3 balls and 1 green ball, the score will be 3 times 10 minus 1 times 5 equals 25. So for each red ball, you get 10 points. For each green ball, you have 5 points deducted, and you have 3 red balls and 7 green balls. And after each ball is selected, it is replaced in the bag. So the probabilities stay the same because you are doing replacement. So what is the expected score in this game? So the way that always works is you could list out all the situations and use the formula expected value is equal to the sum of each potential value multiplied with the probability of it occurring. So what you could do is you could list out all the situations. You could have, so you're selecting 4 balls, so you could have 0 red, 4 green. You could have 1 red, you could have 1 red, and then 3 greens. You could have 2 reds and 2 reds and 2 greens. And you could have 3 reds and 1 green. And the thing is, you can't have 4 reds because there's only 3 red balls in total. So, yeah, there's only 3 red. Oh, sorry. Actually, you could have 4 reds because actually each time you take a ball, it's replaced in the bag. So actually you could have 4 reds and 0 greens. The thing is, you have a 30% chance of getting a red ball and then 70% chance of getting a green ball. So you could have all of these situations. What you do is you would find out the score for each one. And so, for example, here, the score will be negative 20. Here, it'll be 1 red, so it'll be 10 minus 3 times 5, which is negative 5. Here, you'd have 2 red, so you get 20, and then minus 10, so that would be 10. And here, you'd get 30 minus 5, which is 25, which is the case they actually wrote here. And here, with 4 reds, it'll be 40. So these are your scores for X. And then to find the probability of it occurring, you'd have to use binomial probability. So for example, here you do 4 choose 1 probability of success, which is 0. So the probability of success of getting red is 0.3, failure is 0.7. So 0.3 to the power of 1, 0.7 to the power of 3. And you do it for all of these cases. And then you'd add them, you'd multiply the scores with the chance of success. And then you'd add them all up together. And then that will give you your expected value. That's one way you can do it, and it will work. I have tried it this way. I've done it for you. And I got the right answer. So it works. But it's really time consuming and it's only 2 marks. So there must be an easier way to do this question. Well, luckily for you, there is. So, if I erase all equal sides, because this is sort of a multiplication relationship, you don't have any issues with you could do it this way. So like if you've done the James Roos trial paper from last year, you'll see there was actually a question where it was similar to this question, but they had a power, like it was like 2 to the power of x or something. And then you can't do it this way if there's a power relationship, because it messes things up. You have to do it the way I just told you, which is to actually use the formula that of each score multiplied with the probability of it occurring and then adding it up together. But because this is a multiplication relationship, you can use it this way. So our probability of getting a red ball is 0.3, and our probability of getting a green ball is 0.7. So from 4 balls, what is our expected number of red balls? Remember, n, our expected value, is the number of trials multiplied with the probability of it occurring. So if we have 4 balls, our expected value of how many red balls we get is going to be 4 times 0.3. So we expect to get 1.2 red balls. And we expect to get 4 times 0.7, 2.8 green balls. Just using our sort of formulas for finding expected value. So the expected number of red balls we expect to get is 1.2, and the expected number of green balls we expect to get is 2.8. So therefore, our expected score for the entire game is going to be, since we expect to get around 1.2 red balls, our average of red balls is 1.2, our average of green balls is 2.8 out of 4. So notice that this adds up to 4. Our expected score is going to be 1.2 times, we get 3 points for, we get 10 points for how many red balls, and then we have, we subtract 5 points for every green ball. So if we do that, we'll get 12 minus 14. So therefore, our expected score, our average score, is going to be -2. And if you did it the other way that I just told you, you'll get -2 as well. I've tried it myself. You can try it for fun if you want. It works. But this is a much quicker way of doing it. Just finding out what the expected number of red balls you expect to get and the expected number of green balls you expect to get will give you the answer. And then using that, plugging it into sort of the formula of how many points you get. Alrighty, so that is the end of all the sort of revision questions we had that I've planned for you. So we'll finish up today's lecture with exam tips now. So one of the biggest tips I have for you guys is to take your time in the exam room. Like, I know it's really tempting to rush, but just remember to stay calm and make sure to breathe in and out and take your time. Make sure you are reading the question carefully, underline bits of sort of key information. Make sure you are checking your answers and also double checking your answers, and making sure you sort of stay calm and get the question right on your first go by avoiding silly mistakes that are caused by rushing. Like, it's so important. There's like a saying I like to use: quality control is good, but quality assurance is better. So you might be confused by what this means if you didn't do business studies. It's sort of some terminologies we learned in business studies, but basically the gist is that fixing mistakes by double checking is good, but being proactive and making sure you get the question right the first time is even better. So make sure you sort of aim to get the question as accurately as possible without silly mistakes on your first go. Another tip I have for you guys before your HSC exam is to make sure you keep in mind the perspective of who's going to mark it. So make sure you are making your marker happy. So they're going to be examining, so they'll be looking over and marking so many different papers. They'll be doing thousands of papers from all across the HSC students who sit those papers. So they're going to sort of like really tired from looking over so many papers. So you want to make sure you make it easy for them to sort of see you're working and make it clear for them to understand what you've written, and don't like sort of annoy them. Don't make your marker go to the effort to reward you. Make it really easy for them to give you marks. So write big and write neatly. Make sure your numbers are legible. So a lot of the times when you're writing, you want to keep it as neatly as possible, because sometimes you might like to write like 2 like that, but then that might confuse with a Z or something like that. So the way I like to differentiate between a 2 and a Z is I like to put a little line through the Z to sort of differentiate between a Z. And also don't confuse your pluses with T's. Like it's really easy to sort of accidentally make a silly mistake if you do something like that. So I like to write a T like that. And the plus I like to make sure it's like a plus. So just be careful. Write largely and leave lines between sections of working. Don't make it really difficult to follow. Don't use cursive if you can. Write in foundation, because for maths it's easier to read. And when you're graphing, make sure they're big enough so you can sketch key features on them. They should be around 1/3 of a page big. Okay, my next tip is to attempt every question, because as the saying goes, you miss 100% of the shots you don't take. So if you miss a question or if you skip a question, you're not going to get any marks from it because you didn't even attempt it. So attempt every question. Make at least an effort to scrape some marks from that question. But on the flip side, keep writing. Do not let yourself get bogged down by a difficult question, because that's going to impact the rest of your exam paper. You only have 2 hours. So if you are struggling on a difficult question, don't get stuck on it for more than a minute. Like worst case scenario, just skip the question, then come back to it later, because you want to make sure you're doing the other questions as well. So don't like be stuck on a particular section. Just make sure you keep writing. So some final words. You only have less than a month left until your HSC. So now's like sort of your chance to shine. Make sure you don't give yourself the chance to have any regrets. Try your best, put everything you have. You only sit the HSC once, so you want to try your best. And at the end of the day, if you tried your best, you did the best you could, you have no room for regrets. So just try your best, and yeah, take the opportunity to sort of put everything you have into these final sort of weeks before the HSC. Do a little bit of maths every day from now until the exam. Remember, maths sort of is like a muscle that you train, so don't let sort of the skills you've been acquiring die if you neglect it. You can sort of do a little bit and just stay calm. And remember that you do have support networks. You are supported. You have your teachers, you have your fellow students, we have the 80 Notes discussion page. So make sure you keep in mind, you're not alone in this. You have support networks. You have people around you who are sort of forming that support network to help sort of facilitate this sort of difficult period with you. And yeah, remember that successful people aren't necessarily gifted. They work hard and they succeed on purpose. So try your best. Don't leave any room for regrets. And yeah, that brings us to the end of this lecture. It's been such a pleasure sort of doing this revision lecture with you. Thanks so much for coming. Good luck for exams, and I wish you the very, very best for your HSC exams. You guys will definitely smash it, I have no doubt. And yeah, thanks so much for coming. And yeah, all the best. Fingers crossed for your HSC. Good luck again, and thanks once again for coming.